Hello and welcome. In this presentation, I'm going to discuss about nodal analysis with voltage sources. Now, there are two cases that you may encounter in analyzing a circuit using nodal analysis. The first case is if a voltage source is connected between the reference node and a non-reference node, set the voltage at the non-reference node equal to the voltage of the voltage source. So you can see here a voltage source, VA, connected to the ground or our reference. Here, the negative terminal is connected to the reference node, and the positive terminal is connected to the non-reference node V1. So according to case 1, since we have here the voltage source VA is connected to the ground and to a non-reference node, we can say that V1 is equal to VA. That should always be the case. The second case is if the voltage source, whether it's dependent or independent, is connected between two non-reference nodes. The two non-reference nodes form a supernode. So in this circuit, we have VB. Its terminals are connected to two non-reference nodes, V1 and V2. So if that happens, a voltage source connected to directly connected to a non-reference nodes, then that voltage source forms a supernode. And you can also say that if you apply KVL at the supernode composed of V1 and V2, you will find out that V1 minus V2 is equal to VB. Again, you have to remember in case 2 that if a voltage source is connected directly to a two non-reference nodes, then treat that voltage source as a single node, and that single node is known as the supernode. For our first problem, we are going to solve for V and I. So the problem states find V and I. So the first thing to do in nodal analysis is to assign the reference node and then the non-reference nodes. So I'll denote here V1 and V2. Here we can see that this 3-volt source is connected directly to V1 and V2, hence it forms a supernode. Also, we have to determine assign the polarities of each resistors, plus minus with plus minus. Then draw the current flowing through each resistor. So I'll denote I1 here, then I2 flowing through 3 ohm resistor. We have I flowing through 2 ohm resistor, and then for the 6 ohm resistor, I'll denote this as I3. So again, you have to be aware that it's always the plus sign is where the current must enter, and it goes out at the negative terminal of this resistor. So for our solution, we apply KCL at the supernode. So the currents involved, we have I1 as the current coming in, and currents coming out are I2, I, and I3. So expounding each currents, we have I1, which is equal to 7 minus V1 over 4 equals V1 over 3 for I2. Then for I, we have V2 over 2. Then for I3, we have V2 over 6. So rearranging, we have 7 over 4 equals V1 times 1 over 4 and 1 over 3 plus V2 times 1 half plus 1 over 6 close. So if we simplify that equation, we have 7 over 4 equals V1 times 7 over 12 plus V2 times 2/3. So this is our equation 1. And then apply KVL at supernode. We have we have minus V1 since V1 is directly connected at the negative terminal of V3, plus V2, which is equal to 3 volts. Or we can rewrite this as V1 minus V2 equals negative 3. And this is our equation 2. Now we form matrix. So we have 7 over 12 and 2/3, 1 minus 1 equals V1 and V2, and this is 7 over 4, our first constant, and negative 3, second constant. So by using your calculator, the results for our node voltages, we have V1 equals minus 0.2 and V2 equals 2.8 volts. So therefore we have V as our V1 equals negative 0.2 volts, and I is equal to V2 over 2, hence I is equal to 1.4 amperes. By the way, V2 is, we have 2.8, then 2, so I is equal to 1.4 amperes. For the second problem, find V1, V2, and V3. So the first thing to do is to assign the reference nodes, and the non-reference nodes are already designated. Okay, so as we can see, we have here 2 supernodes. So I'll denote this as supernode 1, and this is supernode 2. Then assign the polarities of each resistors, plus minus, plus minus. Then the currents. So this is I1, I2, and I3. Okay. Here we can see that we have 2 supernodes intersecting. This 6 ohm resistor now is already isolated. In other words, it's already short-circuited because of these 2 nodes. These 2 supernodes are intersecting. So it's just like this. So we have here a 2 non-reference nodes short-circuiting the 6 ohm resistor. So if this is a node, so a node can be stretched forming a short circuit. So So this is SN1, supernode 1, and then this is supernode 2. So they are forming a short circuit against this 6 ohm resistor. So these are the other resistors. That's it. So again, the 6 ohm resistor now is being isolated due to the short circuit formed by the intersecting supernodes. So we can apply KCL at supernode 1 and supernode 2. So we have 0. There's no currents flowing in to the supernodes, and the rest currents involved for the 2 supernodes are I1 and I2. And if we expound both currents, each currents, we have 0 equals, I'll just write it, I plus I2 plus I3. For I we have V1 over 2, and then for I2 we have V2 over 4 plus V3 over 3. Again, it's equal to 0. So this is our equation 1. Now we can apply KVL at our supernode 1. We have V1 minus V2 equals 10. For each supernode, to make an equation out of KVL, just take the potential difference or the difference between the 2 non-reference nodes, and the resulting difference must be equal to the magnitude of that voltage source. So for supernode 1, we have V1, since V1 is connected directly to the positive terminal, and then minus V2 since V2 is directly connected at the negative terminal of this 10 volt source. So this is our equation 2. And similarly, KVL at supernode 2, we have V2 minus V2 rather plus V3 equals 5I. So, or could be rewritten as V2 minus V3 equals negative 5I, and we also have to recognize that I is simply V1 over 2. So V2 minus V3 is equal to 5 times V1 over 2. Hence we have 2.5 V1 plus V2 minus V3 equals 0. So our equations now, we have for the first equation we have 0 equals V1 over 2 plus V2 over 4 plus V3 over 3, equation 1, and then V1 minus V2 equals 10, equation 2, and lastly we have 0 equals 2.5 V1 plus V2 minus V3. It's our third equation. So we can form a matrix now. 1/2, 1/4, 1/3, 1 minus 1, 0, 2.5, V1, V1, V2, and V3 equals 0, 10, and 0. So using your calculators, should have V1, V2, and V3 equals 70 over 23 minus 160 over 23 and 0.6522 volts. For the third problem, obtain the node voltages V1, V2, and V3. So first things first, we have to assign our reference node, and non-reference nodes are already designated. Then we can see here that we have two voltage sources forming a supernode. So this is the node is 10 volts as our supernode 1, and then this 20 volt source is our supernode 2 SM2. Also, by case number 1, if we have here a voltage source, for our circuit we have this 12 volt source connected to a non-reference node and reference node, hence this V2 is equal to 12 volts because the positive terminal of this 12 volt source is directly connected to V2. Then by KVL at supernode 1, we have the voltage differences minus V1 plus V2. Minus V1 because V1 is directly connected at the negative terminal of the 10 volt source, and V2 is connected directly to the positive terminal of this 10 volt source. So we have V1 minus V1 plus V2 equals 10, or V1 minus V2 equals negative 10. This is our equation 1. Then KVL at supernode 2, we have V2 minus V3 equals 20. However, we already know that V2 is equal to 12. Therefore, we can now solve for V3 minus V3 equals 20 minus 12. So V3 is equal to minus 8 volts. And also from equation 1, we have V1 minus V2 equals negative 10. Therefore, V1 equals minus 10 plus 12. Okay, we have to remember that V2 is equal to 12 volts. So V1 is equal to 2 volts. Answer.